Hey guys, so today we're going to cover Avogadro's law, fourth period. I know you've done this, just bear with me, it'll be quick. And then we're going to go into ideal gas laws, and then we're going to go to gas stoichiometry. I do need you to keep in mind you will still have a test this week. I understand we are experiencing outages. We are at my house. I'm sitting at my in-laws' house right now recording this, so I understand there will be plenty of time once it comes back on to deal with it. However, it is going to have to be dealt with this week at some point, and if you don't do it, you're going to get a 0. Okay, so starting this video for Avogadro's law, we're looking at volume in moles. This is the same Avogadro that had Avogadro's number. So as you notice here, moles increase, so does volume. This is a direct relationship. One goes up, the other goes up. One goes down, the other goes down. They go the same direction. So they are directly proportional. The equation, let's write it here. V1 over N1 equals V2 over N2. Remember, if they're divided by, they're directly proportional. If they're multiplied, they're inversely proportional. To solve these, we just do cross multiply, we divide, and then we solve. You do need to keep in mind, like this question says how many additional moles of helium must be added. So once you solve for N2, then you have to subtract them because it wanted to know how many more there were. Okay, so that's the same question. Let's do a different one. I've got 0.58 moles of gas and 0.11 moles. And it says before the reaction. So this is N1. This is N2. Also, it says produces. Our initial volume is V1, and it wants to know the volume after. So I've got 2.1 liters over 0.11 moles equals V2 over 0.58 moles. Remember, we cross multiply. We divide by the one with the variable. So I do 2.1 times 0.58, and then I'm going to divide by 0.11. And I have V2 equals 11 liters. Remember, they are directly proportional, so it was almost 6 times, so therefore it should be about 6 times, which it is. Okay, so here we're combining them all into one law, and this is how we get the ideal gas law. This is the ideal gas law. I know it's not read, but it is very important. I need you to write it down. I need you to make sure you know the ideal gas constant. It is always the same number. Sometimes students ask me, how do I put all those letters into the calculator? Y'all, you've never put letters into the calculator. We're not going to start now. Okay, so R is always 0.0821. P is pressure, except now it has to be in atmospheres. T must still be in Kelvin. Liters, volume must be in liters. Before it could have been milliliters or liters. The biggest thing is this one has to be in atmospheres because our R value is in atmospheres. Okay, so here it's just going through all of them, how we get it from the ideal gas law. Okay, they're solving some. Let's go ahead and solve one. So remember, PV equals nRT. The biggest thing is that you keep in mind pressure must be in atmospheres, temperature must be in Kelvin, volume must be in liters. We solve for the missing piece. The way we know it's this one instead of the combined gas law or one of the other gas laws is because there's only one of each thing. I've got 1 mole, I've got 1 pressure, I've got 1 Kelvin. That's how I know I can't use the ones with 2 of the same type because then it doesn't work. All right, so my pressure is 1.37 times V. That's what I'm looking for. Moles, 0.0845. Sorry, not 0.845 times 315 Kelvin. Okay, some people at this point are confused about how we're doing the units. Here's the deal. This Kelvin crosses out with that Kelvin. This moles crosses out with that moles. I'm going to divide the atmospheres over here. I'm going to divide by 1.37 to get rid of it. This is divided by 1.37. So then my atmospheres cancel. Okay, so in our calculator, I'm going to put 0.845 times 0.0821 times 315 divided by 1.37. And I get that V is equal to 15.95 liters, which rounds up to 16.0 liters for sig fig purposes. Okay, let's do another one. This one wants pressure. So we've got P is our, we don't know, times volume, 8.5 liters equals 0.55 moles times 0.0821. Liter atmospheres per mole Kelvin times, this time we're at 305 Kelvin. Again, our pressure must be in atmospheres. So we're doing 0.55 divided by 0.0821. Sorry, times, not divided by. Times 305. Now divided by 8.5. And I get that my pressure, I need 2 sig figs, is 1.6 atmospheres. Okay, please ask if you have questions. You do need to reach out, although there's a good amount of practice in mastering chemistry. It has been moved till Wednesday. That is where it will stay. All right, here's another one. We've got PSI, though, and Celsius. So, remember, pressure must be in atmospheres. Temperature must be in Kelvin. So, remember, there are 14.7 PSI in 1 atmosphere. Calliope. Sorry, y'all. My dog is going where they're not supposed to go. Okay, so for the pressure, I got 1.65 atmospheres times 3.2 liters equals N. That's what I'm looking for. Remember, R is always 0.0821. And then 273 plus 25 is our 298 Kelvin. Okay, the biggest issue we have on ones like these, we're dividing by 2 numbers, the 0.0821 and the 298. So, okay, you're going to need to put that side in parentheses for the bottom. That way you know how to do it. I get that N is 0.22 moles. That's how much moles are in that basketball. Okay, they walk you through it. 0.22 moles. Okay, here's another one. Same thing, except we've got Celsius again, but now we're in millimeters of mercury. You still must get that to atmospheres. I'm not going to work this one. There's another one. This one has grams. So that means you need to get grams to moles, and you need to get Celsius to Kelvin, and you need to get milliliters to liters. Then you will solve it in atmospheres, and then you will solve back to millimeters of mercury. All right, now we're doing molar mass with this. I do want you to remember that molar mass is just grams per mole. So if they gave us grams, we're solving for moles. So ignore the grams for now. We're going to say the pressure is, okay, we're going to divide 886 by 760. I get 1.17 atmospheres times 0.225 liters equals N times 0.0821 times number 55 plus 273 is 328. Zero 0.00978 moles. Okay, remember, molar mass is grams per mole. We do molar mass equals 0.311 divided by 0.00978 moles equals I get 31.8 grams per mole. Okay, so then if they ask me what sample of gas that was, we're looking at something that's either about that mass, which is sulfur, or it could be something that's diatomic, like oxygen gas. All right. This one, you're doing the same thing, except this one gives you milligrams instead of grams, so you have to convert it to grams. Remember, molar mass is always going to be grams per mole. All right. So gases do not always behave ideally. They will behave ideally when they are at high temperatures and low pressures. Otherwise, they behave like a real gas, which is what's normal. And the kinetic molecular theory doesn't really work for real gases. Okay, as far as partial pressures go. Partial pressure, so here in this example, we've got helium and neon in a container. The whole percentage has to equal 100 because that's what percentages equal. So if I've got 80% of helium and 20% of neon total, they have to equal 100. So here is Dalton's law. You do need to write that down. Okay, and all you do in Dalton's law is you add them up, and then they need to equal the total. So here, they gave us a total. Partial pressure is this, and neon is this. We add those and subtract them from the total to get the partial pressure of argon. That one we just went through. Let's do this one. Partial pressure of 24 torr. The mixture has a total pressure of 745. So I have 745 torr equals 24 torr plus the pressure at H2. So I'm going to subtract my 24 from my 745. And I get 721 torr is my partial pressure for hydrogen. All right, so what this is useful for, again, it's when we're talking about diving or you're going up into the mountains to keep your oxygen level the same percentage so it stays consistent with our bodies. Okay, too much of oxygen is not good. Same thing, too little of oxygen is not good. So our percentages need to stay the same, that relationship they have. Okay, same thing with oxygen. So here we're taking the percentage at 2% oxygen with a total pressure of 10 atmospheres. So in order to find the partial pressure component, you take the piece times the total pressure. The piece will normally be a percentage. You need to put that in decimal form, which is why they did 2 divided by 100. Okay, they just did that one. Let's do this one. So 5%, So that's 0.05. So what will the total pressure be? I'm looking for P total equals 0.21 atmospheres. So to solve for P total, I'm going to divide by 0.05, and I get that P total is 4.2 atmospheres. Okay, so you take your fractional percent, times it by the P total, the pressure of the total thing, then you will get the partial pressure of that component. Okay, there are situations where we have to do stoichiometry, which is what this is. The reason we need to do stoichiometry, it wants to know liters of oxygen. It gave us 294 grams. And it does not say it's at STP. It is in fact close, but not quite. So we use stoichiometry to get moles of oxygen. Then this is in oxygen. So we plug that into PV equals an RT. Okay, so first let's get 294 grams of KClO3. Of course, I didn't bring home my periodic table, but handy dandy, I've got my phone. So 39.1 plus 35.45 plus 16 plus 32. Okay, so this is 122.55. Okay, so again, we're trying to get moles out of this. Okay, so I got 3.60 moles of O2. So then we do our pressure. Don't forget it must be in atmospheres. So I have 0.993 atmospheres times volume, I don't know, 3.60 moles times 0.0821 times 305 Kelvin. All right, so 3.6 times 0.0821 times 305 divided by 0.993, and I get that the volume is equal to 90.8 liters. Now, is that a lot? Yes. Is that a good amount of oxygen? Yes. All right, we can also collect gas over a water. This is how we figure out water vapor pressure. Here are water vapors at different temperatures. What we normally do is 25 Celsius, but this table is for everything. So this table may need to be used for Mastering Chemistry's homework, but it won't need to be for the test. Okay, we've already talked about how we find moles. That's the same equation, it's just rearranged. And that's similar to the problem I was doing. Also remember STP. STP is 1 atmosphere at 0 Celsius, so 273 Kelvin. And the molar volume is that 1 mole is equal to 22.4 liters at STP. So you will need to write that down. That is only in ideal situations at STP. It must say STP or it could say standard pressure, standard temperature. It could tell you 1 atmosphere. It could tell you 760 torr or millimeters of mercury. Okay, so the volume is directly related to moles, not to mass. Remember, mass is dependent from the periodic table. So here, that's that problem I worked earlier. 90.7 is what we got. Okay, let's do this one at STP. How many grams of water are formed when 1.24 liters times 22.4 liters over 1 mole? Okay, it's just a form of how we're solving our stoichiometry problems. So I get 0.998 grams of water. Okay, here's another one. How many liters of oxygen? So this is going the opposite direction. You should be able to handle that. So all I did was add that 1 mole is equal to 22.4 liters is now a conversion factor. Instead of just grams and moles being a conversion factor or mole ratio being a conversion factor, we also can use liters at STP for moles. Okay, now we're just going into the different types of air pollution. There's a lot of different air pollutions. If we were in class, we would go into more detail, but to keep this short, we're going to go ahead and wrap this up. If you have questions, please reach out to me. You'll have a good day.